one more example from chapter 4, number 22. This is a classic projectile motion problem. So it says a small ball rolls horizontally off the edge of a tabletop that is 1.2 meters high. It strikes the floor at a point 1.52 meters horizontally from the table edge. A, how long is the ball in the air? B, what is its speed at the instant it leaves the table? So I want you to pause the video and take some time to try this out on your own. So filling in, drawing a picture of what this scenario is describing, writing down what we know, preferably in terms of our 10 kinematic variables, writing down what we want to know, and writing what tools we have. So take some time to do it. It's not as much fun as just passively watching a video, but I promise it is good for you, even if you just get stuck and stare at it for a minute. At least spend some time thinking about this. So go ahead and please pause the video. Right, I'm gonna have to trust that you did that. This is so hard, but let's see. So drawing, it says it's a small ball that rolls horizontally off the edge of a tabletop. So we have a tabletop and say the ground. And the ball rolls and it says horizontally off. So it's a flat table. And we can also sketch out the path, right? Remember, it's going to be a curved path. Nice parabolic path. All right, so that's a good picture to get started. Then we can figure out, what do we know? Well, the first thing you always want to fill in is the acceleration in the X and Y direction, because as long as something is moving through the air, you automatically know that acceleration. So in the X direction, it's going to have to be 0. In the Y direction, it is negative g, or negative 9.8 meters per second squared. So that's where you always want to start. Now, there's also some other numbers given to us in the problem, right? It mentioned the tabletop is 1.2 meters high and strikes the floor at a point that's 1.52 meters horizontally from the table edge. So you could fill that into the picture. 1.52 meters, tabletop, 1.20 meters. Now these are distances, so these are going to be related to our displacements, right? X minus x naught, final minus initial. If it starts at 0 and finishes at this 1.52 meters, we can write this in as a positive 1.52 meters. It has moved in the positive direction. What about in the y direction? This one we have to be a little bit careful on. It is a distance of 1.2 meters, but has it moved in the positive y direction or the negative y direction? Indeed, it has gone down. So this is one where we need a negative 1.20 meters. All right. This is looking pretty good, but notice we only have 2 givens on either of these, which is a bummer. We need at least 3 in order to be able to solve for the other variables. But there's another clue tucked into this problem, some implicit information there, and that's when it says horizontally, rolls horizontally. If it's rolling horizontally, that tells you something about the initial velocity. What does it tell you? It tells you the initial velocity is purely horizontal, right? If this is our initial velocity back here, then it is only going in the x direction. In other words, in the y direction, the initial velocity is 0. This is like the demo where we launched the ball forward. There was no vertical velocity, it was all horizontal. This is really comforting because now we have 3 out of 5 of our y variables, which will help us out. So now we can look at what we want to know. So part A, it says how long is it in the air? And what is its speed at the instant it leaves the table? So how long, that's going to be our time. And what is its speed at the instant it leaves the table? Leaving the table, notice that's not going to be when it hits the ground. That's going to be at the very beginning. How fast is it going? I'm going to stop sharing now that we've written all of that down there. Now this is a little bit bigger. And I apologize for that bright spot right in the middle. But I promise that that says 1.52 meters. Not really the ideal there. I don't know if there is a good spot to have glare, but here we are. Okay, so for tools, if we want to solve for time, we know that we can do that in the y direction because we have enough information there. So we want something that involves displacement, initial velocity, acceleration, and time, something that does not involve final velocity. And there's one equation that matches that. In terms of y, that would be our y minus y0 is equal to v0y times time plus 1/2 a sub y t squared. And so we notice if we want to work with this, the initial velocity in the y direction is 0. So this term is going to just go to 0, and we'll have y minus y0 is equal to, we can plug in for the ay and negative g, so minus 1/2 g t squared. And what we are trying to solve for here, remember, is our time. So I'm going to multiply by -2 divided by g. -2 times delta y all divided by g is equal to t squared. So then I can take the square root. And right now this looks a bit scary because I'm taking the square root of a negative sign. We don't tend to like that. But are the math police going to come arrest us right now? Are they going to get really upset? Well, let's take a look. Because we're careful with our signs, we remember our displacement is negative. So we're going to be okay here. We could plug in some numbers. And we'd get -2 times -1.20 meters divided by, and the g here is 9.8. We've already accounted for the negative sign. So this is positive 9.8 meters per second squared. We need to square root that. That will give us our time. So when you calculate this out, you should get something along the lines of 0.495. With what units? Seconds. And we can double check. We do have 3 significant figures, so that is good. Now what about for part B? We want to find the initial velocity, but we already said in the x direction, we only had 2 out of the 5 variables, not 3. So what do? Well, that's where we're very happy that we solved for time, because as I mentioned in an earlier video, time is our crossover variable. So the fact that we've solved for it in the y direction means that we now know it in the x direction. So we now have 3 out of 5 of our variables. So I think we could even maybe fit this over here. So notice in terms of x, we need something with displacement. We want to find the initial velocity in the x direction. Acceleration and time, it's going to be the same equation, something that doesn't have final velocity. Cool. So we could do our displacement in x, delta x is equal to v0x times time plus, this is going to get a little bit tight, 1/2 ax t squared. The reason I'm okay with cramming this a little bit is what's the value of the acceleration in the x direction? It's 0. So this whole second term is just 0. It goes away. Only because we're in the x direction, flying through the air. So what does this mean? It means that we have delta x is equal to v0x times time. And that's it, right? If we wanted to, if we weren't convinced it was purely horizontal, we could write this as delta x is equal to v0 times cosine theta 0 times time. And maybe that will help you see that if we're firing it horizontally, what's the angle with respect to the x-axis? It's 0. And what's cosine of 0? That's just 1. So that would disappear. We can now solve for this initial velocity if we divide by time. So we'd have that the initial firing speed is the displacement in x divided by time, which we just solved for. And so we can plug in those values. So 1.52 meters divided by the time, 0.495 seconds. And so if you calculate this out, you should get 3.07 with units of meters per second. All right, so in this example, we demonstrated how the x and the y directions are independent of each other except in regards to time. And time can act as our crossover variable. This problem could have just asked for the firing speed, and you might have been at a loss if you were focused on just the x direction until you remembered that the y direction can help you get that time, and time can help you then solve things. So, believe it or not, time is on your side. This fully completes chapter 4, and it has some really neat problems. So thanks for coming along with me for this ride.